Thank you very much for the nice introduction, Ulrich Adriani. Thank you very much that you stay all the day through the sessions and guide me through this last presentation, which deals with corrosion protection. I missed around the whole agenda in the 2 days a little bit more about corrosion protection, but so finally we can finish it with a theme, with a topic on quality control in the passive corrosion protection. The coating inspector. I would like to emphasize that the paper you can, if you are interested in this issue, you may download from the PTC homepage, is written together with 2 colleagues of mine. The one is Thomas Löffler, who is with us today in the audience. Thomas is from a German pipe coating supplier, and Andre Grassmann, he's working together with me in Open Grid Europe as a pipeline manager. To those of you who hear the first time the name Open Grid Europe, I would give small key figures of our company in a brief summary. It was established as E.ON Gas Transport in 2004 and renamed as Open Grid Europe in 2010. Open Grid Europe is one of Europe's leading natural gas transmission pipeline network operator and operates approximately 12,000 kilometers of gas pipelines in Germany and 30 compressor stations, housing 1,000 compressor units with a total capacity of approximately 1,000 megawatts. It has a sole responsibility for the operation, control, expansion and marketing of the transmission pipeline network, and it has a total number of 1,400 employees. The headquarters is in the center of Germany in the town Essen. A small table of content to prepare you for the paper. I would give a history, look back to coating failures or deviations from specifications. The history of coating quality assurance in our company, coating inspectors, short form is the CI, how we developed that in Open Grid Europe. Then a field case study from a pipeline that was constructed in 2012 gives the results and findings from this field case study and what is going on with a coating inspector in the future as a forecast. So I would like to give you some figures from the horror cabinet of the coating systems applied on some of our pipelines. If you look on the left photo, there was a typical example for raw material selection. The specification says there to use 2 tapes. The first tape, the inner tape, is a PE tape backed on both sides with butyl rubber. And this first tape is wrapped in two layers circumferentially around the field joint area. And the second tape is a PE layer with one side with butyl rubber. And this is also wrapped 2 layers, minimum 50% overlap. And only this field coating compound makes a full self-amalgamating system, a coating system, which meets the specifications. What went here wrong, the people who applied this field joint coating took the wrong material. They took the outer tapes and wrapped it 4 times. So what you can see, you can very easily pull this off like a tapestry on the wall. It has no adhesion at all to the field joint area. On the right photo, you see a wrinkle formation of a tape system. This wrinkle may occur if you choose the wrong tension of the wrapping machine. If the tension is too small, then you may create such wrinkles, and the formation of a wrinkle may lead in the worst case scenario that water may penetrate through this wrinkle and reach the steel surface, and due to the shielding effects of cathodic protection, corrosion may occur beneath this field joint coating area. This is typical what we find when the surface preparation is not done properly. The surface preparation is two issues what we try to achieve. The first is the cleaning of the steel surface, and the second is to get the correct roughness of the steel surface, that we get the best adhesion between the coating system and the steel surface area. On the left photo, you can see that there has been done no preparation at all. What was done in this area, there was a peel test, and the peel test says you have a full adhesive break. Normally what we would try to achieve is a cohesive break. That means the coating system shall break within itself. What we do not try to achieve is that the coating system completely adheses, lost its adhesion from the steel surface, and you can see this on the both pictures, that the entire coating system has been pulled off this surface area. Here are three examples from GRP, glass fiber reinforced epoxy systems. What you can see here is a pipeline that is three-layer polyethylene factory coated and with additional mechanical protection with glass fiber reinforced, which is also applied in the factory. And in the field there was applied a glass fiber epoxy compound. And what happened here? You may imagine that the first staff was preparing this, is doing the surface preparation with the sandblasting, and the coating team was preparing the glass fiber epoxy and was laminating the system, and the wind carried the grid blast from one field joint to the that was just prepared, that was just under preparation, and it got trapped in the material, in the epoxy compound. If you see this, there was mud that was laminated in the GRP field joint coating, and you may not detect with the Holy detection some pores or coating defects, but what you will get by these areas, it is a conductive path to the steel surface, and it will give some amount of CP current for the later CP system, and we will see later that these impurities will give a certain percentage of current pickup of the entire system, coating system. Insufficient laminated GRP, you can see pieces of the glass fiber that is totally loose from the field joint area. Here there has no epoxy been laminated at all, and with a completely insufficient result of the field joint coating. Here are some photos of two-component hot airless polyurethane sprayed coatings. We use these for fittings or for valves, for isolating joints, but also for areas in compressor stations where we have operating temperatures exceeding 50 degrees. Then polyurethane is the material of our selection. You can see a minor coating thicknesses on the saddle of the valve. Here you see blistering on a section where the temperature conditions had not been met, or where the humidity was too high, or where the dew point conditions have not been met according to the specification. Then you find these blisterings in the polyurethane coating. So we asked then one day ourselves, are we looking here for the needle in the haystack, or are we seeing this tip of the iceberg, and the rest of the of the failures we have not found is below the sea level, and we decided and made us clear with this situation that it's more like this. It is not a single incident we are looking for with these coating failures, but it is something like the tip of an iceberg. I would like to give a small look back to the coating quality. Average coating resistance. The average coating resistance is a cathodic protection figure that gives you a benchmark of the coating quality you achieve in the field. And what I've done here in this table is I have summarized some pipeline commissioning data from the CP, from pipeline data, and from the year of construction. You can see that we had in the 80s and in the 90s, we had pipelines that had this average coating resistance, which is a figure that does not relate to the, that does not depend on the CP data, whereas the protective current density depends on the CP level of the on potential. This is this is independent on the CP level applied to the system. This average coating resistance was for the year of construction between the 80s and the 90s between 0.1 up to 1.5 or 2 megohm per square meters. And in 1997, we first carried out so-called current drainage tests on pressure test sections. We injected the current, and this measured on and off potentials and measured the current, and we gave certain threshold values in order to find, with this very quick current drainage test, to find larger coating defects on these pressure test sections. With this technology, we could increase the average coating resistance to 10 times higher, so produce more quality. And in 2006, we gave a threshold value of 10 to the power of 8 ohm per square meters, which is now put in German codes and standards from the DVGW. This is also one of our partners here at PTC. They produced the worksheets WG12, 20, and 28, where we gave this average coating resistance, where we manifested the this 10 to the power of 8 ohm per square meter. With this fixed threshold value, we could again increase the average coating resistance, which is our benchmark figure in the coating quality, in measuring the coating quality. So we then asked one day, we have, everything is perfect, we have certified people who apply the systems in the field, we have certified material that is tested by DIN, that is tested by DVGW, but the only puzzle that is missing in the system is the quality of the system on site. And so we started to give some concept planning. The motivation was to create preventive quality control to avoid future risks and imponderables for the pipeline integrity and maintenance expenses. And the idea was to create quality control by qualified, competent people, external or internal, and we decided not to give the responsibility to the pipe laying contractor that he subcontracts coating inspectors. We decided to that it is the best way that our own personnel should represent the owner's interest at the best. So we trained then in-house those candidates for the future coating inspection. We provided them with measurement equipment and drafted checklists for the quality control. So then we prepared this expert portfolio. His tasks the coating inspector shall perform in the field, was planning, implementation, monitoring, and documentation of the pre-qualification of the coating staff commissioned by the contractor prior to the start of construction activities, examination and documentation of visual integrity for all factory-coated pipes and fittings, planning, implementation, monitoring, and documentation of the coating quality for the applied field coatings, inspection and acceptance of the generated quality documents. So that are the documents the pipeline contractor or the subcontracted coating companies are obliged to produce. Examination of all field coatings regarding quality, suitability, and confirmation to our company standards. Claiming all quality deficiencies, e.g. coating defects. Coordination, monitoring, and documentation of executed current drainage tests to verify application of a flawless coating. Now I would like to go to present you this field case study. This was a pipeline, loop pipeline. So we had once in the 70s laid the first pipeline, and we had already had the right of ways to construct a so-called loop pipeline in parallelism to the first one. And this pipeline was starting in Sannarts in Hesse and went across 67 kilometers to Rimpa in Bavaria. And typical distances for well stations are between 10 and 18 kilometers. Material was L485 MB with 3-layer polyethylene. Nominal diameter was 40 inch. Pipeline length was 18 meters. Weight per pipe was 7.5 tons. Operation pressure was 100 bar, 1 meter of earth covering. The time schedule was the engineering started in Open Grid Europe in April 2009 and went throughout to January 2012. Construction was in 2012 and commissioning of the pipeline was also 2012. So you can see here one of our own trained coating inspector doing some field tests on the field joint coating. You can see here the typical damage of a porcelain factory coating due to transport. There were metallic chains who fixed the support and the valve on the lorry. That is clear, making the defects in this area we would like to avoid. We had then a couple of inspection reports prepared by our coating inspectors. We had two CIs working in the two lots of this pipeline section. And we prepared a total number of 122 reports. 80 reports were without observation, so good result. Mechanical damage during pipeline construction dealt with 19 reports, so 60% of that. Total 122. Coating application failures were found in 17 cases, and damage due to transport was in 6 cases. So if you take these 42 things that are here, a total number of 42 test reports, then you can say these 19, half of these were caused by welding activities. The welders put their welding equipment like brushes and welding machines on top of the pipeline and destroyed the PE coating. Nearly 100% of these coating application failures relate to polyurethane coatings, wrong mixing ratios. The applicators did not consider the temperature conditions on site. Nearly 100% of the damage due to transport belong to valves and fittings. We saw this photo with the fixed chains where the metallic chains have fixed the valve on the lorry. And there were two indicators, two key indicators. The first key indicator was the measurement of the average coating resistance on the pressure test sections, and we were lucky we had a second pipeline in Bavaria that was similar long as a loop Sanatz-Rimpa, was constructed at the same time and has the same diameter, but we had there no coating inspectors that supervise the coating quality on site. And what you can see is a list of this RCO. You remember, it shall be larger than 10 to the power of 8, and you see the loop Sanatz-Rimpa, all pressure test sections that have been checked with current drainage tests did meet the requirement, and only one pressure test section of this benchmark pipeline did meet the requirement. So all these other pressure test sections, several 10 kilometers, have been labor intensive, be checked with close holiday detection in order to find the coating defects. The second key factor that we used was the so-called EITEP method. EITEP method is a method that was developed in Germany to detect small coating defects on a pipeline. It is similar to the DCVG method, direct current voltage gradient measurements, that you can find also in the international standard. We carried out this EITEP method after one winter period so that we are sure the pipeline has sufficient ground contact and we find all coating defects. And we put on potential of -9 volts to -12 volts in order to, with this negative on potential, to find also smaller coating defects. And on the loop Sanatz-Rimpa, there was one defect each 11.5 kilometers, and only on the benchmark pipeline we had each 750 meters one coating defects. So these two key indicators, the average coating resistance and the measurements from the EITEP, made us sure that we had made the right decision to give quality control and extra coating inspector, and that we have been done the right steps in order to increase the coating quality on site. And I would like to come to the conclusion and forecast. We have demonstrated that we could improve the coating quality on site significantly. Trainings for CIs to supervise coating activities for buried piping on compressor and metering station has been extended. Now, this case study was on a pipeline. What we find on the pipe, or what we do on a pipeline, we nowadays do permanently also during construction on compressor and metering stations. We expand the responsibility for the CIs to check quality and standard of above ground paintings also. All paintings that are applied in order in line with ISO 12944, part 1 to part 8, above ground coatings of filters, of compressors, of above ground fittings that are not with these typical systems that are for buried pipelines, but that are normally used with, normally applied with paints. CI activity today became integral part of OGE's expediting strategy. We contract third-party coating inspectors and send them to factories where the factory coating is applied. And we have also a draft of a technical standard at DVGW, and this is the logo of the DVGW, describing the qualification of CIs in Germany. So this paper shall describe, it will be published this year, it will describe the skills, the qualifications, the duties, and the, well, everything about the coating inspector, what his expert portfolio shall be. And this is the end of the presentation, and I'm free to answer your questions. Thank you very much for paying attention.